tools from Stanford to do the word-to-word, co-occurrence relationship, statistical modeling, everything possible. And then we have introduced a method to determine the priorities. And then we have proposed a resource-constrained hybrid scheduling model which takes into account these priorities. And remember that when there is a disaster, these priorities are not fixed. They keep changing, right? So you have to have a model which can update these things in real time. So what's our approach? We have data preparation, we extract the information, annotate, do the tweet classification, and then arrange the rescue schedules. Okay? So I have collected several data. So let me talk first about the tweets on Hurricane Harvey and Hurricane Irma. We have these tweets from 26 August to 31st August 17, September 10 to September 17. We have done the pre-processing. So what pre-processing we have done? First, we remove all the non-English tweets. It's very hard to translate. In Texas, for example, right? People use Spanish and so on. Filtering noises, we have removed the duplicates, remove all the special characters, stop words, some jargons people use. Okay? And then we have also corrected the spelling check, right? So we integrated the Bing to correct the spellings, when we write tweets, right? Many times we have spelling mistakes. We have also used custom dictionary to convert all the abbreviations, right? In the tweets, it's 140 characters, and now, of course, 240. People use abbreviations, right? So, of course, some misspelled abbreviations are kept because generally that's how we use, right? So that gives some more information. We have manually labeled 5,000 tweets into 6 different binary classes. Rescue needed, DCW, water needed, injured, sick, flood. These are the classes which have been defined by FEMA. Okay? From these, about 68,000 pre-processed tweets, and then of course, a tweet can belong to multiple classes. So we are not classifying one tweet to only one of this. It may be classified to multiple of these classes. Okay? So how we have done? We have used the text embedding. We have used bidirectional long short-term memory and STM. We have an attention layer. We are trying to use those words. And remember, convolution layer, of course. We have pre-trained the word vectors, as I mentioned, crisis and glow, which are the tools from Stanford to do the word occurrences and statistical modeling of those words. So we have done the external text embedding. We extended some auxiliary features. So 140 words are not enough, right? So we have put some auxiliary features from the tweets and used that as an input. Okay? So we have used word level deterministic differential attention mechanisms to identify the words which are closer in relationships and so on. I'll show you what are those. So first is the architecture. So you see that I have input layer. You do the text embedding using glow and crisis and also the natural language NLIP. Then we do LSTM, of course. Then we have attention layer. Then auxiliary feature input, another LSTM. So that's our deep learning convolution layer, dense layer, sigmoid model, and then we have the predicted output. So we have, of course, these parameters we have taken into account, like for text embedding, we have about 300 dimensions. So we have tried to, play with these dimensions. VLSTM layer, 2 layers, 300 hidden units. Dense layer, 3 layer, 2 layers are 150, 25 units. So we have played with all these parameters within this deep learning model. Okay? I'll not go into the details. You can see the paper. And then the auxiliary feature input. So as I just mentioned, the tweets have this restriction of 140 characters. And now, of course, 280. So we have taken into account, like people use extra punctuations, right? And that has a meaning. We use right? We use all these emojis to specify the meaning of the tweet. So we have converted those into the text information. We also have a greater use of numeric characters in those tweets. So as you can see here, this example also has images, right? Now, if we have images, we have converted those images and tried to extract some semantic information. So here you can see that water rising quickly, please help as soon as possible, and there's an address, but you can get some more information like what is the situation right now. And this is, again, you see that some textual information people use, right? So we have seen those things in the tweets. So auxiliary feature inputs, so as you can see that, we have taken into account all these auxiliary inputs, like digit versus length of the digit versus the word, punctuation versus the length, punctuation versus words, capital versus word. So we have taken into account all these auxiliary features in this learning. Then we do the priority determination, and in the priority determination we have two parameters, alpha I and double j. So one is the feature vector denoting the weight of the variables, and then the other one is also the weather. So you see that the weather changes, right? Whenever there is a flood, for example, the flood level can rise, it can go down. So we have to assign the proper weight, and that's very important when people are doing the rescue operations. Okay? So we try to assign those weights to these different labels, and I'll show you an example how we have done that. Then, how you extract the location. This is very important if you're trying to schedule a rescue operation. We need to know approximate location. And the tweets will not give you in all the tweets the location information. So try to geolocate them if available. We use Stanford Named Entity Recognizer, Google Map API, as much as we have done with all those tweets, try to see if we can get some location information. If there is no available, what we do? We go to the user's profile and try to extract some information from user profile. Okay? Now, then of course the rescue schedule, we have to see that what are the resource constraints, how many people are available, how many boats are there, right, and what other resources. Generally, there are teams, right? They cannot just rescue everybody. So we have to see the priority of each task, and that priority has to be recalculated using the priority function, and then you might see that there's a new request has arrived in that window. Then you have to recalculate those priorities. Then environmental situation can become severe in time. So you have to assign different weights to those environmental parameters. So the priority again needs to be recalculated. So this is an ongoing process. Okay? So we have proposed an algorithm. I will not go into the details, but I'll show you first the experimental results. Okay? We have done a lot of experiments. So the very first one, 4,900 manually labeled tweets are used. So you can see that the student has taken 4,900 manual tweets, tried to label them, okay, for training. So then the testing has done with 20% of the tweets. So we discarded labels like injured and sick. The reason, there are very few tweets which talk about injured and sick in those tweets which we have collected. Okay? And I'll show you the graph that how many percentage of those are there. So we have implemented our machine learning ensemble model, try to classify and compare. So you see that most of the tweets are like help needed, flood, water needed, DCW, sick and injured are like very few, right? 0.3%. So it's not good to use and train those if you don't have enough tweets, right, regarding those. So let's talk about the results and compare with others. So first is about precision, recall, F1 score, accuracy. I showed you those formulas. We have used the same. So this is the Hurricane Harvey and Irma. The logistic regression, precision is very low, recall is high, F1 score. Overall accuracy is 84.5. SVM, CNN, and this is our model, okay, using the attention layer. So you see that the accuracy in identifying those tweets into one or more of those 6 categories defined by FEMA. Okay? By the way, I heard that there is a similar agency in India also. I don't know the name, though somebody mentioned it. Okay, so here is the evaluation matrix for individual classes. So you see that how accurately from those 7,000 tweets we could categorize into health, flood, water needed, DCW, weighted average. And that's why FEMA is interested in this, right? Because if they can do this, they know, right, which tweet, where is the person, whether they can fall into those categories, right? Precision, recall, F1 score, accuracy. So you see that we could do this with a very high accuracy, trying to identify those tweets and categorize into one or more of these categories. Okay? Then we have now these 17 different disaster data sets, and this is from Crisis NLP, this is from QCRI. So you see that logistic regression, SVM, CNN, this is our model, the last one. Nepal earthquake, California earthquake, typhoon, and then it's a combination of those. Okay? So again, I'm just showing you that how accurate we are with respect to others, okay, in terms of accurately finding those. Here, all those models, this is our model with precision, recall. Of course, this is all this Crisis NLP database, this is Crisis LAX, which is actually, so this is this. This has 15 different disasters data set, okay? So we have taken all those and tried to see how accurately we can do things. So again, if you see the accuracy of our model, the last one, you see that we are very much, if you compare with others, we're the best, right? Now, why we have done this? We have now the system which have been trained now by 17 or 18 different disaster data sets. Whenever there is something happen, God forbid should not be, but if there is a tweet, there is no time to train the system. It will immediately do and classify, right? Because we have taken all the data sets which are available. Okay? So now, of course, comes the scheduling, right? How we are using this information. So this is not just about correctly, accurately classifying, but how the FEMA can also go and use this in scheduling. So of course, first come first serve is not the right thing, right? Whenever there is a disaster. So we have developed this multitask hybrid scheduling algorithm, and for the evaluation purpose, I'm showing you, this is like a simulated thing, right? Because we don't have the information about the rescue. So we have simulated that, we have taken the tweets, real tweets, but then simulated the rescue operation, okay? So there's a 174 rescue seeking tweets are found, 72 hours of data frame, we have taken that window, and then we have performed some upsampling so that we have not just 134, we have made it like 550 rescue seeking tweets. So this is just to show the graph here that when the tweets arrive, you see that sudden burst, right? At some time, maybe something happened, many tweets start arriving, okay? And then this is how the tweets arrive in that time period. So we have calculated the priority of each tweet on a scale of 10 using those four classes. Flood, water needed, DCW, and sick or injured. Okay? The weight of those classes are assigned 1.5, 2.5 for all this, okay? 2 and 2.5. And for the environmental features, of course, we have used a random distribution between 0.5 and 2.5. Remember that we didn't have that information, right? So we're just showing you I'm just trying to show you the simulated information. Then we have implemented this algorithm, of course, on a multi-processing system. Okay? And 10 and 20 rescue units are used for the evacuation purpose. So if you see here, the FCFS, of course, is like a base case, right? Because generally it's scheduling that works the best. So with 10 processor, maximum weight, average is 3.73 with 20 processor. Mean average with 10 processor, 20 processor, 2.53. So if you see that this is the one which we have developed, 4.47, very close to first come first serve, right? That basically means it's doing very well. Of course, we are not doing first come first serve, but for correctness. 3.02 for the 20 processor, 2.24 here, and then 1.31 here. Okay. So this is the average waiting time. And this I'm showing you how well we are doing with multitask hybrid scheduling. You see that this is the line here. Okay. So we try to do much better than with other algorithms which are out there. So for the rescue, a real world scenario, so we have selected the first 10 tweets on the Hurricane Harvey, about 20-mile radius, 12 p.m. of 30th August 2017. The map, you see that this is the control center from where they're basically trying to do the rescue operation, right? And these are the victims, right, who are stranded and to be evacuated. So I'm trying to examine this, how effective is our algorithm with just 2 rescue units, right? So again, I have given the weights that if it's about flood, 1.5, water needed 1.5, DCW 2, sick or injured is the highest weight, 2.5, right? And you can see here that in the tweet there's a flood as well as water needed, there's no DCW but sick and injured, right? So you may have a tweet falling into those 3 categories. The demo weights, how we are giving those, of course, again simulated. So storm 1, road damage, forecast storm, forecasted flood. Okay, starting time of the rescue mission is 2 p.m. The speed of the boats or vehicles which are there, 20 miles per hour, and then there is a break of 30 minutes. This 30 minutes I got from how these rescue units are working, okay, from the paper. That every time they rescue, they have to wait for 30 minutes and then they go for the next operation, okay. And then this is, so because of the time, I just run through this. So there are tasks, and their tasks may have different priorities. So you see that priority score is high here, then this is the next. Both these tasks arrive before this, right, 7. So we have to prioritize, and then we try to calculate the distances from that control center, how far they are, how much it will take to go there, how much is the waiting time from the request, and then the first person is served, and then of course you see that after that it takes only 15 minutes, there is some distance to be covered, there's a duration to go there, and so on, and it just shows, to the agency that how much time it will take, and this is just, I'm showing that these people are rescued together, these people maybe rescued first, and these are the priorities, okay, you can see those numbers. I'll just stop here. So again, what is the objective? The objective was very simple. We collect all these tweets, we are getting all these tweets. The agencies like FEMA has this question, how to find categories of people which they have defined. Okay, in their document, they have very clearly that whom they are going to rescue first. Here, I'm trying to get that information from the tweets, okay, correctly, and then use that, prioritize those, and try to generate the rescue scheduling, and then how to rescue people. Okay. So I have taken an appointment now with FEMA, and I'm going to show this system which we have right now about 85 to 90%. If you have interest, I can show you during the lunchtime how it is working. It has everything. We already trained the system. So as soon as there's a new tweet, we fetch in real time and categorize. Okay? That whether it is about one of those categories or more of those categories. Okay? Future work, still we are looking into this, how to find precise location information. Because if the location information is not correct or is not there, and that's a challenge. Okay? How to assign these appropriate weights. You saw those numbers are given 1.5, 2, and 2.5, and so on. How to model the bus time. Suddenly something happens, so many tweets will come, right? How you can immediately prioritize those things. And then, as I said, that you're developing a full feature application. I just attended the governor's advisory for the flood management. And last year, the Missouri had a lot of these flood warnings and flood, so they want to have some system that can help people. Okay? So now I can stop. I'm sorry, I think I've gone a little beyond my time. So if you have any question, otherwise we can take off. Yeah. Right.
But I could have a page with a list of all 6 hashtags for each category, so that you wouldn't have to do machine learning.
Well, so what I'm trying to do is the way people are writing the tweets, the hashtag is not enough. It's not about the keyword. I can say somebody is flooding a message, right? The flood does not mean anything there. Okay, so hashtag will not help.
We could have pre-assigned hashtags for each category that we are trying to.
Now, how you get those categories? That's what I'm trying to define.
But that's DC, W, we can have a hashtag women, children, elderly.
Oh, people don't do that, right? See, that's what I'm saying. People are right. This is like a, disaster, right? People are just setting some information immediately. They're not saying any DC. They don't even know DC numbers. That's FEMA's thing. That's, as a general public, I don't know. Even I came to know about those things when I was doing there.
Thank you, Dr. Sanjay. I now request Dr. Tanmay to present him with a token of thanks.
So I'm sure that you have a lot of questions. So since we are running weekend schedule, so
I'm here the whole day.
Yeah, so you'll be here around till 5 p.m. So if you have any questions, you can ask. Okay. Thanks a lot.
Our next speaker is Dr. Shubhashis Sengupta, Managing Director and Technology Research Executive at Accenture. He received his PhD from Indian Institute of Management, Calcutta. Today, he will be talking about approaches in domain knowledge graph construction and consumption.
Am I audible? I don't know. What are my kids? Sincerely. So my name is Shubhashis. I lead the Accenture Labs AI R&D. Okay, my time is up. And I'm glad to be here and presenting to you about some work in the area of knowledge graph. I think you were part of this buzzword called knowledge graph. We heard some very great lectures on social network analysis, but I'll take another side of it is how do you essentially get the world's knowledge together and create something which is an interesting structure, and how can you use this in many kind of AI and ML or other works, right? And of course, the bulk of the work is done by my colleagues, Anirvaz and Vivek, in collaboration with universities like CMU, but I get to do the work here. So that's being like a lead of the lab. So before I go there, a couple of minutes of overview of what we do at Accenture Labs. I don't know, you must have heard of Accenture, but I don't know whether you've heard of Accenture Labs. So we are a corporate R&D division, like many others here. We have 300 plus researchers all over the world, and I belong to the Bangalore unit. And these are the kind of works that we do in the labs. AI is one of the obviously a foundational stone, if you say this. And these are the kind of work which goes on. My team primarily works in the area of conversational AI, but also in the area of what we call euphemistically artificial general intelligence. I know it's a very loaded term, but one of the things is around how do we actually take the world's data and structure it, and who does it better than Google, right? But in the industry space, what can we do from there? So when we get there, we get started on what is meant by the knowledge graph. Knowledge graph is nothing but a triple, right? And a conglomeration of triples. So you have got from the linguistic sense, you have a subject, you have predicate, and you have object. You're connected. The predicate denotes some kind of action or some other things, and you conglomerate these subjects and objects together. And you have things like, for example, here you can see things on Barack Obama and others. Who was Barack Obama? What were his children doing? His wife and stuff like that. Right? And what you use knowledge graph for, and the greatest example is Google. So you search anything, and you can see this knowledge vaults coming up, and you could actually have all the military information, so you can go on and click happily getting all the information from there. The curating such a knowledge graph is a difficult problem. So I'll talk a little bit about three fundamental things of knowledge graph. How do you curate knowledge graph? Especially the 80% of the world's information, and that goes for the industry also, is unstructured. There's no database that you can really query and join and create something. Right? The second thing is that how do you query? And one of the biggest advantages that knowledge graph brings to the traditional RDMS system is that it actually allows a lot of fundamentally very different queries, taking things from different sources and finding out how they link together. And third is completion and reasoning, right? Every knowledge graph is incomplete because you cannot possibly, even if you scour to multiple sources, you cannot possibly get all the data from all the events at the same time, and it varies with the time. So there will be some things incomplete. How do we complete them? So the rest of my talk is actually about some of these things. How do we curate, how do we curate, how do we query, and how do we infer or